So if we think about points in the coordinate plane, we can represent them with rectangular coordinates. Sometimes we call that Cartesian coordinates. Cartesian or rectangular, doesn't matter. Polar, we use the r value and the theta value. And the r value is just the distance from the origin out. Typically, we think of it as distance. Like we saw last time, you don't have to. You can do that negative r value if you wanted. But typically, the standard form, we're going to go counterclockwise rotation and a positive distance. Don't have to, but that is primarily what we do. So over here, we want to convert this over from Cartesian. And again, it's not obvious necessarily that this is Cartesian or rectangular. So sometimes it's helpful if you want a reminder to put an R for rectangular or C for Cartesian, doesn't matter. A P for polar. So we want to convert this over. This direction is a little harder. When we're going from polar over to Cartesian, it was very simple because we had these straight up equations that if we had the polar, we just plug them right in there, we get the x, we get the y, and we're done. Like that was very simple. Going the other way is a little bit more work. So we want to find r. So we know that r squared is x squared plus y squared. So we can do this kind of thing. And 1 squared is 1, and root 3 squared is 3. So we get r squared is 4. So we could choose r to be positive or negative 2. Typically we'll choose it to be positive 2. So we have those two choices. And then to get to theta, we are going to use the tangent of theta is y over x. So in this case, the y is root 3, the x is 1. So we're going to say tangent of theta is root 3. And again, we have a trig equation. There's lots of options for a trig equation. When we're thinking about this trig equation, you should be thinking about the unit circle. And you should be thinking about the 12-sector unit circle. So the one that looks like a clock. All right, this is the one where every sector is 30 degrees. So the 12-sector unit circle. And where is tangent equal to root 3? Pi over 3. So these two angles right in here, so this angle and this angle, both of those will have a tangent value of root 3. So remember that tangent is the same as slope. So the slope of this line is root 3. And the natural choice for theta would be this pi over 3 angle right here. That would be the natural choice. You could use the other one, which is what? 1 pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3. So you could use 4 pi over 3 and then a negative r value to do either of those. Okay, so we're going to choose theta to be pi over 3. So our standard representation of this point then, let's see, we had our r value. So our standard representation would be r comma theta. This would be the standard representation. That's in polar. That would be the one that is preferable. But if we wanted to be contrarian, we could say, hey, let's go to 4 pi over 3 and use a negative 2. And of course, there are an infinite number of other choices as well. So both of these are representations of that point in polar form. Same point. Now let's look at some curves in polar. Polar gives us a whole nother swath of curves that we can graph really easily. First, we're going to look at our basic ones. And so by a basic curve, we usually take the coordinate variable and set it equal to a constant. Like when we're in the xy plane, we want to know that x equals a constant, it's a vertical line, y equals a constant, it's a horizontal line. Same idea. When you get into Calc 3 and you have spherical coordinates and cylindrical coordinates, same idea. You want to come up with, well, what's the basic What's the set of basic equations if we let the coordinate variable equal a constant? Well, if we let the theta equal a constant, we get a circle centered at the origin. That's simple. All right, so if we graph r equals 3, that means we want all the ordered polar points, r comma theta, we want all the points where r must be 3 and theta can be anything. So that would give us a full circle centered at the origin. So radius equals a constant will give us a circle centered at the origin of that constant's magnitude. Because if we did the contrarian thing and said r equals -3, we'd still get the circle. Yeah. If we take the other coordinate variable, which is theta, and we set that equal to a constant, we're going to get a diagonal line. So if theta is a constant, that means r can be anything. And when we're in two-dimensional polar, we allow r to be negative. So if theta was, say, pi over 3, we'd get all these points over here when theta is pi over 3 and r is positive. And then we get all these points over here when theta is pi over 3 but r is negative. So if you allow this negative r thing, you get the full line for theta equals a constant. If we set the two coordinate variables equal to each other, we get an Archimedean spiral, r equals theta. As theta increases, r increases. So we get further and further away from the origin. And that's going to create that spiral. So as theta is getting bigger and bigger, r is getting bigger and bigger, which means r is pushing us away from the origin. We'll get a spiral. And again, those are our 4 equations. Those are the equations that allow us to go back and forth between these two perspectives, the Cartesian perspective and the polar perspective. Most of the time, when we write a polar equation, we think of r as the dependent variable, and we think of theta as the independent variable. And so we will write r as a function of theta. R is a function of theta. Again, that's backwards from what we do with x and y, but it is what it is. So r comma theta. So we're writing the first coordinate as a function of the second, as opposed to Cartesian where we write y as a function of x. So it is what it is. Now, this direction is always harder when we start with polar and we want to get over to a Cartesian equation. We have to be a little clever here. And so these two equations are going to represent two very common strategies. So right now we have, well, actually, let's rewrite. The first thing we notice is that these equations, when we're looking at our x's and our y's, we have cosine and sine. We don't have cosecants or tangents or secants. So we want to get rid of those trig functions. We'd like to have sines and cosines. And if we multiply both sides by sine, it becomes pretty obvious what this equation is. Our sine of theta is y. So this is just a horizontal line at -2. So now you know how to draw horizontal, or how to create the equation for a horizontal line in polar. That's it. That's a horizontal line in polar. What if we wanted the line y equals 4? What would the equation be for y equals 4?
R equals 4 cosecant theta?
Yeah, r equals 4 cosecant theta. Yep, exactly. So that's how you draw horizontal lines. This one's going to be very similar. This is 4 times secant. Let's get rid of the secant, write it as a cosine. So this is going to give us a vertical line. So if we wanted a vertical line at -7, all we do is put a -7 right there, and we'd have r equals -7 secant. So horizontal and vertical lines, that's how we draw them. And yeah, I guess I was going to mention this other technique for converting, but we'll get to it. It's actually a little later. So circles in polar. Well, we talked about the simple ones. The ones that are centered at the origin look like that. Just r equals a constant, centered at the origin. Desmos can graph in polar also. No problem. Here is going to be a generalized circle. In this class, we are only going to look at partially generalized circles. Instead of looking at the general circle, what we're going to do is look at these circles that are tangent to an axis. So instead of combining sine and cosine together, we're just going to look at the individual pieces, just to keep it simple here. So the most common circles that we are going to see are going to have this form. And if we have r equals a constant, 2a is just a constant, times sine, we're going to get tangent to the x-axis at the origin. And if we have r equals a constant, so that part 2a, that's just a constant, times cosine, we're going to get tangent to the origin on the y-axis. Okay, so these are the two that we are going to see. Tangent to the y-axis, tangent to the x-axis. Those are the two. So now we have to figure out a way of, remembering which is which. So let's look at an example. All right, so there, hopefully, as you do a few of these, you start to recognize that, oh gosh, that's going to be a circle. Whether it's tangent to x or y, we'll figure it out. But if you can just know at least that you're dealing with a circle, that's going to give you a little advantage. Okay, so now we have our 4 conversions that take us back and forth. These 4 conversions right there. So we want to target those. We want to target those and try to create them. Let's see. Are you not going to let me right click? Double click? No? Yeah, it doesn't matter. Okay, those are our 4 equations. You have them memorized already. So we want to somehow try to create one of those equations or more than one of those equations from here. And so we have to do things. We have to do things to this. We know that in that those equations up there, r squared is equal to x squared plus y squared. So over here on the left, we don't have an r squared, we just have an r. But if we multiplied by an r, we get an r squared. And then we look at the right and we see, oh, we have a sine of theta. And up in the equations, there's not just a sine of theta, it's r sine theta. So here's one of the classic techniques to convert from polar to Cartesian. We multiply both sides by r. And if we multiply both sides by r, then all of a sudden we can convert back to x's and y's really easily. Right? Because r sine theta is y, x squared plus y squared is r squared. Boom, we got rid of the r's and the thetas. So we multiplied everything by r. And if we want to figure out what this circle is, what's the technique we use from algebra? Begins with a C, complete the square. So we divide by the coefficient of y and square it, add that to both sides. So the coefficient of the linear term is 4, chop it in half and square it. And now we can write the equation of this circle in standard form. We're going to have x squared plus y plus 2 quantity squared equals 4. So this is a circle that has center 0, negative 2, and it has a radius of 2. 0, negative 2, and a radius of 2, so it looks... I didn't like that. That was close. Whoa. Is undoing stuff over there? Okay, let's try that again. Circle of radius 2. That was better. That was better. Okay, so there we go. There's our circle of radius 2. That looks like a circle of radius 1. Good call. Let's make it. My drawing is so bad right now. Okay, roughly there. Circle of radius 2, centered at 0, negative 2. So circle of radius 2, centered at 0, -2, there it is. And so again, as you do more and more of them, oh, it's a sine, it's going to be tangent to the x-axis. Cosine would be tangent to the y-axis. Notice that this is below the x-axis because it's negative. If it was a positive, it would be above the x-axis. So we're going to see that pattern. We'll look at a couple of them in Desmos in a minute. Same idea here. So if we have a constant times sine or a constant times cosine, we know it's a circle. How do we find the equation? Well, we're going to multiply both sides by r, and we'll convert this over to Cartesian. So if we multiply both sides by r, then we know that we have x squared plus y squared is equal to 2 times x. We put everything on one side. We leave a little gap so that we can complete the square. And what number are we going to add to both sides? A 1. We divide the coefficient of x by 2. We get a -1, and then we square -1 and get +1. So that's our strategy. Complete the square. So this tells us that the standard equation for this circle is that, which we now know has a center of 1, 0 and a radius of 1. So let's see if this circle will draw properly. That's better. So there's our circle. Center 1, 0, radius 1. So positive cosine puts it on that side. If it was a negative in front, it would pop it to the left. So cosine is always going to be tangent to the y-axis. Sine is always going to be tangent to the x-axis. All right, let's. So if you go into Desmos and just play a little bit, you should be able to get pretty darn comfortable with a lot of these basic types of polar things, polar graphs. So if you come over to the wrench, the default is that you're in the XY graphing mode, the Cartesian graphing mode. If you click on polar, now you're in polar. Come over here. If you graph r equals a constant, ding, there it is. If you did r equals -2, you'd have the same circle. If we do r equals 2 cosine of theta, we're there. And if we put a minus in front, it's just going to move it to the other side of the y-axis. If we change that to sine, sine with a negative is down, sine with a positive is up. So if you play around a little bit with that, you'll get pretty comfortable. Oh my gosh, I think I feel like it's gotten louder.
I feel like they're adding more passes too.
Yeah,
It's like 2 before. Now
he's
we're
getting a
getting 3
little
or 4,
obsessed
yeah.
with it. I saw him yesterday afternoon, like cruising around on it. I'm like, dude,
He wants to really puts on his
they're really clean. It's like, whoa.
He's enjoying his
He's enjoying his job.
with Walkman and block and get off the freaking Zamboni.
All right, so here we have a more general trig equation. The graph, we're only going to look at basic graphs. Lines, circles tangent to the origin or centered at the origin, and then cardioids. We're only going to look at those 3 basic graphs. We're not going to look at really weird graphs.
What would a problem look like?
We'll get to that. So we just have to, going from Cartesian over to polar is actually pretty easy because you just replace x with our cosine of theta and y with our sine of theta. So you can get to a parabola pretty easily. But we're only going to look more in details at lines, circles, and cardioids. Oh my. Lines, circles, and cardioids. So here, we'll get to the cardioids on the next slide, but here we just have some general equations. We know that this one's a circle centered at the origin of radius 2. This one, we have no idea what it is. We don't care what it is. But we want to convert this from polar to Cartesian. There are the equations. This direction is always harder. Going over to polar is easy because you just replace all the x's with that and all the y's with that. Right? Instantly, you're in Cartesian. excuse me, you're instantly in polar if you replace all the x's with that and all the y's with that. So here we have to be a little more clever like we were in the last one, where we multiplied both sides by r, and that worked. Here we don't know yet. We certainly don't want cotangents and cosecants. We want sines and cosines and perhaps a tangent. So one thing we could do is rewrite the cotangent as 1 over tangent. And we can rewrite the cosecant as 1 over sine. So now at least we have the trig functions that are showing up in our conversions. And when we look at the sine, it's all by itself. It doesn't have an r with it. But if we multiplied both sides by sine of theta, we could do this kind of grouping. And this is good. So that helps because r sine theta is y. So now we have y on the left, and on the right we have 1 over tangent of theta. Tangent of theta is y divided by x. So this is going to give us y equals, oh, a parabola. So there is the equivalent Cartesian equation. So now we know what the graph of this is. This is actually a parabola that opens to the right. You know, it's the standard parabola to the right. Dustin?
Are there no r's in the tangent? Because it would be like r over r and they cancel out?
Yes, exactly. Right? If you replace this with r sine theta and this with r cosine, yeah, exactly. Yep. Yeah, so the r is always attached to a cosine or a sine. Now how about this one? This one we already know what the graph is. It's a circle of radius 2 centered at origin. But how do we convert this one over to Cartesian? What do you think we're going to do? Square both sides, which is totally different than multiplying both sides by r. So we had some where we multiplied both sides by r. That's a common strategy. But this time we don't want to multiply by r because then we'd have a single r on the right, which is back where we started. A single r is no good. We want the r to be squared, or we want the r to be grouped with a sine or a cosine. But squaring both sides is great. Squaring both sides puts us in that situation. Now we have an r squared. R squared is x squared plus y squared. And so this is going to be the circle centered at the origin of radius 2, which we should have known, right? X squared plus y squared equals a constant is a circle centered at the origin. So that's our strategy. If we have r equals a constant, we square both sides. All right, the last type of curve we're going to look at is a cardioid. So if we look at these equations, the cardioids look like a circle plus a constant, right? This, we already talked about a constant times cosine or a constant times sine is going to be a circle, right? Constant sine. But here we're adding a constant of the same magnitude. And it's really helpful going into this to know that if we add a constant of the same magnitude that it's a cardioid. Like, that's going to just help us tremendously. And I'll show you why. So as long as these two constants have the same magnitude, it doesn't matter if there's a plus or a minus. It just changes the location of the cardioid. But that's going to be a cardioid. All right, as long as these magnitudes are the same. Now, if you were to change the magnitudes, you end up getting something called a limishon, which we're not going to deal with. But if you graph a limishon, like you make the coefficient way out in front, the constant out in front, bigger, it kind of flattens out that cardioid dimple.
Lazy cardioid.
Lazy cardioid. And here you get an overambitious cardioid if you put something that's, well, you can't even see it there. If you put a constant out in front that's smaller in magnitude, you're going to get this little bubble on the inside. So you get this overambitious cardioid, and you get this limishon that has a bubble in the middle. But if it's exactly equal, you get the dimple. And then if you change the magnitudes, it either gets flatter, the lazy cardioid, if this is bigger, and the overambitious cardioid, if this one is bigger. You get the little bubble. Okay, so when you're dealing with cardioids, the thing I want you to notice is that there are 4 intercepts. And the intercepts are always going to form a capital T. So intercept, 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 intercept. So if we know we have a cardioid, then we can say, oh, let's find the 4 intercepts and then connect the dots. So if we look at the shape of a cardioid, there's going to be the 3 intercepts there, and then 1 extra intercept down there. So we have 2 intercepts, so 4 intercepts total. We should be able to connect the dots. Notice that when you have your intercepts out here, these 2, that the cardioid is round. It's very round. It pushes past those intercepts and then comes down. So we should be able to graph this pretty easily. So let's just notice this first. Okay, so here's a cardioid with the coefficients have the same magnitude. So that means it's a cardioid. And the sum of those magnitudes is always going to give you sort of this spine distance right here, 4 units right there. But here are the 4 intercepts. All right, so let's figure out how we find those. Similarly, there's 4 intercepts for this other one, and it's going to form a capital T. It's going to be, depends on the orientation of it, but if you get those 4 intercepts, you just connect the dots. If you know it's a cardioid, you should be able to connect the dots and build that little cardioid, that kidney bean. So how do we find them? Here's what we do. So let's look at the first one. All we do is rotate theta from 0 to 2 pi. That's all we do. So the first one over here, we let theta equal quadrantal angles from 0 to 2 pi. So the quadrantal angles, 0, pi over 2, pi, 3 pi over 2, and 2 pi would be back to 0. So we just need these 4 points. All right, we have 2 axes. We're just going to look at the 0. We're going to look at the angle theta that brings us to each axis. So all we do is plug those 4 numbers in, and we'll find our 4 intercepts. Plug in 0 here. Cosine of 0 is 1. 2 minus 2 is 0. So there is our first point right there, 0, 0. We rotate 90 degrees. Pi over 2. Cosine of pi over 2 is 0. 2 minus 0 is 2. So that says when your angle is pi over 2, you go 2 units away from the origin. So that's right there, 2 units away from the origin. Then we rotate, we're at pi over 2, we rotate to pi. Cosine of pi, -1. -1 times -2 is +2. 2 plus 2 is 4. So we're going to be at 4. So when we're at an angle of pi, we go 4 units away, which puts us right there. And then we do our last one, 3 pi over 2. Cosine of 3 pi over 2 is 0. 2 minus 0 is 2. So when we're at an angle of 3 pi over 2, so here's our angle, 3 pi over 2, we go 2 units away. That builds the capital T. We connect the dots, bubbling it out, and that's it. And the dimple is always going to be at that middle point where you have the 3 on the 1 axis. So for the second one, very similar. Start at 0. Cosine of 0 is 1. Cosine of 0 is 1. 2 plus 2 is 4. So when your angle is 0, you're 4 units away from the origin. Rotate to pi over 2. Cosine of pi over 2 is 0. 2 plus 0 is 2. So when you're at pi over 2, you're going to go 2 units away from the origin, which puts us right up here on the y-axis, right there. Rotate over to pi. Cosine of pi is -1. 2 minus 2 is 0. So in the direction of pi, we plot r equals 0, which is the origin, right there. Last one, 3 pi over 2. Cosine of 3 pi over 2 is 0. 0 plus 2 is 2. So when we go to an angle of 3 pi over 2 down below, we go 2 units in that direction. That puts us right here. Connect the dots, we've got a cardioid. So they all are going to have this capital T, which will guide us. Let's do this one just by rotating here. When theta is 0, sine of 0 is 0. 3 plus 0 is 3. We should be at 3 comma 0 right there. Go up to pi over 2. Sine of pi over 2 is 1. 3 minus 3, 0. Over to pi. Sine of pi is negative 1. No.
No, 0.
Sine of pi of 0. 3 minus 0, 3. 3 units away from the origin in the direction of the pi. In direction of pi. Get down to 3 pi over 2. Sine of 3 pi over 2 is negative 1. That makes us positive 3. 3 plus 3 is 6. So we're going 6 in the 3 pi over 2 direction. So there's our capital T. Piece of cake. But it is a piece of cake because we know in our mind that it's going to be a cardioid. So we just plot our 4 points and we're good to go. This one, when theta is 0, sine of 0 is 0. 3 plus 0 is 3. We go 3 units in the 0 direction. Plug in pi over 2. Sine of pi over 2 is 1. 3 plus 3 is 6. So in the pi over 2 direction, we want to go 6 units away. So that's our second point. Then we get over to pi. Sine of pi is 0. 3 plus 0 is 3. So we go 3 in the pi direction. And the fourth point, when sine of 3 pi over 2 is negative 1. 3 minus 3 is 0. There's our fourth point right there. There's our capital T. Connect the dots. Okay, so we've got these 4 key points for a cardioid. They're always going to create this capital T. Let me do the first one here from scratch, and then you guys can do the second one. So it all boils down to just making this table of values starting at 0 and just wrapping yourself around the unit circle until you get all the quadrantal angles. Cosine of 0 is 1. 4 plus 4 is 8. So in the 0 direction, we're going to go 8 away from the origin. So this is our first point right there. Plug in pi over 2. The cosine of pi over 2 is 0. 4 plus 0 is 4. So that says in the pi over 2 direction, go 4 units from the origin. That puts us up here. Plug in pi. Cosine of pi is negative 1. We get a 4 minus 4, which is 0. So in the pi direction, go 0 units from the origin. And then our last one, 3 pi over 2. Cosine of 3 pi over 2 is 0. 4 plus 0 is 4. So in the 3 pi over 2 direction, go 4. If you don't get that capital T where you have 3 dots on one axis and 1 on the other, you did something wrong. If you know you have a cardioid, that's always going to be the case. 3 dots on one axis and 1 extra dot on the other axis. And then we just connect them. And so you don't have to get fancy. We just want, a rough shape.
If our rough shape looks real bad, but we have the T, do we get points?
Yeah. Yeah, your rough shape can be real rough. That's fine. When you're drawing them, you just have to remember when you're going through these outer dots on the T, it just bubbles out, so it creates almost a circle-looking thing on the right side in this case.
It's not going to look good.
No, it doesn't have to look good. All right, try this one. So 2 minus 2 sine theta. But you do have to be efficient at evaluating your trig functions of the quadrantal angles. Sine is the y value, cosine is the x value.
It works, right? It communicates the message.
So what's the R value with theta equals 0? 2. Everyone agree? So plug in theta equals 0 radians, sine of 0 radians, y coordinate in that direction is 0. So 0 comma 2, well, technically in polar, this would actually be 2 comma 0 because it's r comma theta. Even though we plug in the theta first, it feels a little backwards. But that is the point right there. We're going over here. R comma theta. In the pi over 2 direction, what's sine of pi over 2? Sine of pi over 2? 1. And then 2 minus 2 is 0. I know what you meant. So that's going to put us right at the origin. Pi over 2 direction, we go 0 units away, so we're at the origin. Pi direction, sine of pi is 0. 2 minus 0 is 2. We go 2 units away in the pi direction. Last one, 3 pi over 2.
-1.
3 pi over 2 sine is -1. -1 times -2 is 2. 2 plus 2 is 4. So we're going to go 4 units away down there. And then we just connect the dots. So everyone got the same dots? And it's usually easier to draw it, 1/2 at a time.
I'm just gonna give you a heart, man.
Heart,
Is that cool?
that's fine.
Great.
Yeah. Happy Valentine's Day.
It's fun to break that.
Oh, just on time.
Just on time. We're finally there. April, almost May,
This is definitely a class full of dudes.
right? No doubt. Any questions on graphing, lines, circles, or cardioids? We have one section left.
Oh, let's do weird stuff with this now.
Now let's do weird stuff.
Calculus and polar coordinates, I know.
Calculus and polar coordinates. It's only weird if you make it weird. All right, let's see. Calculus and polar coordinates.
Keep the socks on, boys.
Okay, so calculus and polar. We're going to look at two different concepts. We want to calculate slopes of tangents and find areas bounded by polar curves. So the first thing, slopes of tangents. This should look pretty familiar. It should look a lot like what we did up here with parametric. When we did the derivative in parametric, we did the derivative of each component function. We had our x function and our y function. We took the derivative with respect to t of the y, the derivative of x with respect to t. So we did that, sort of derivative of each function. So let's see how that looks in polar. So here, same idea. We want the derivative of y with respect to theta and x with respect to theta. And you're maybe thinking, well, what's y and what's x in polar? Well, here's how we create parametric equations from our polar equation. So our polar equation is r equals some function of theta. So maybe if it was a cardioid, it is r equals maybe 3 minus 3 sine theta, all right? And if we plug that function in here and multiply by cosine and plug that function in here and multiply by sine, we now have the parametric form of the polar equation. So this is going to be the easiest way to get at this. Then we're just doing what we did on Tuesday in 12.1. So we take our polar equation and we build these parametric equations. So we build parametric from polar just by replacing the r. So for example, now that we know has a graph of a circle. That one is a circle. Okay, and we could, calculate what it is if we want, but we don't need to. So we just want to change this to parametric. So parametric says x is equal to r, this is r, times cosine theta. So r times cosine theta. And y is equal to r times sine of theta. So these are the polar, this is the parametric equations for the polar equation. The parametric form of the polar equation. And I don't know, but usually when we multiply sine and cosine, we usually write it as sine times cosine and not cosine times sine. So now we have the parametric form of the polar equation. So there's our polar equation. Here's our parametric form. And now we do what we did in 12.1. In 12.1, we said the slope of the tangent, dy dx, is y prime over x prime. Now in 12.1, we differentiated with respect to t. Here we differentiate with respect to theta. So we're going to differentiate both of those with respect to theta. Now if you're good with trig, you might say, oh, these are related, there are double angle identities that we could convert. You do not have to. But if you recognize that 2 sine theta cosine theta is equal to sine of 2 theta, you could, because that would actually be easier to differentiate than this, which we have to use the product rule for. But you don't have to. So you could convert with double angle identities if you wanted. Let's not do that. So y prime up top, I'm going to treat this as first function that, and this is going to be second function. First function, second function. So product rule says first derivative second. So the first function times the derivative of the second function. The derivative of the second function is negative sine of theta. So that's going to give us negative sine of theta times 2 sine theta. So there's first d second. First derivative second plus the derivative of the first times the second. Derivative of first is 2 cosine theta times cosine theta. So we're going to get 2 cosine theta squared. So there's the y prime. The x prime is pretty simple because we first use the power rule. We bring down the 2 and multiply it by the coefficient and subtract 1 from the exponent. So that's the power rule part. 2 comes down, subtract 1. But then we have to differentiate the base. So negative sine of theta. So we'll put a sine of theta right there. Put a negative out in front. So there is the derivative. That is the slope of the tangent line. So it's the slope of the tangent line as a function of theta. So we would have to know what theta is in order to figure out what dy dx is. But that's it. That's how we do it. So y prime over x prime. How do you get y and x? You take your polar function and multiply it by cosine. Take your polar function, multiply it by sine. So that's our strategy. And again, if you wanted to, you could recognize that these actually are both double angle identities if you wanted to, but you don't have to. It's just another place to go wrong. So, there is another way to find dy dx if you are into horrific formulas.
Yeah.
If you are into horrific formulas, if you are a masochist, you could use this formula for dy dx. My recommendation is to you can use it. Okay. My recommendation is to understand this process though. If you take your polar equation, convert to parametric, and then just do what we did in 12.1, y prime over x prime, that is a functional way to do it that you can actually remember. Convert to parametric, dy over dx. That formula is something no one in their right mind would ever memorize. Uh-oh. So if anyone wants to memorize it, they can. No extra credit for that, though, because that formula is worthless. But one thing that you can see from this formula that's, at least interesting is that
Oh, nothing.
nothing, it vanished, is this. So if you have a polar curve that goes through the origin, it's very helpful to find, you want to find the slope of the tangent wherever, but if your curve happens to go through the origin, they have this nice little summary down here that says, oh, the slope through the origin, we don't know what the angle is, but the radius is 0, r comma theta, is tangent of whatever that angle is. So this angle right here, they're saying is theta naught. And the slope of the tangent line, if the curve goes through the origin, is just tangent of that angle. Okay. Why? Well, if you look up here, they have defined, they've used another, they love to introduce new letters, so there's r equals f of theta. So if you wanted to write this formula like a little neater, if you really wanted to get into this formula, here is how I would recommend writing it. Like, why introduce a new letter? There's no need to introduce a new letter. If you're just going to say r is f, why not just put an r there and an r prime there? There's no need for that extra letter.
With the f, they're doing it because it's f of theta naught, correct? Not just f. So it's f of value, or it's r evaluated at theta naught.
Correct. Yeah, absolutely. Yeah, so, yeah, if we wanted to be super precise, we would write r of theta naught. Yeah. But if you're going to evaluate this whole thing at theta naught, you could be doing, like, here's how I would write it. R equals, at theta equals theta naught. And then you're going to plug theta naught in here. You're going to plug theta naught, plug theta naught, plug theta naught everywhere. But that's the idea. Now, if we're at the origin, the r value is 0. So if we plugged in an r value of 0 right here, if the r value is 0, that's gone, that's gone. And then r prime would cancel with the r prime below it because these are gone.
And you get tangent.
And you get tangent. Yeah. So that's why it's true. It's not that, it's more of an observation, because if you are plugging stuff in, if you have your dy dx, and you happen to be plugging in the origin, r equals 0, and you figure out what your theta value is, you just use this formula and you're going to get to the right place. But that's why it's true, for those that care about why. Okay.
Personally, I'm an X-Man myself.
Why is that page blank?
I think you just duplicated the page.
That's what I'm hoping, but why? It says page 2, and there's also
So
a
you go
page.
from P2 to page 2 to P3. So
Oh, okay, so it is a duplicate.
it's a
Okay.
duplicate, yeah.
Okay.
An empty page. You can
I was
check
worried
for
there
it.
for a second that something vanished,
Yeah.
other than brain cells.
Yeah.
Okay, so let's go ahead and try this. So here we have slopes of tangent lines. Find the slope of the tangent line to the following curve. So first off, it's very helpful to just make an acknowledgement when you have a polar curve and when you have a parametric curve. So that is a polar curve. Polar curves have r's and thetas. So we've got a polar curve there. And we don't know how to graph this polar curve because this is a multiple angle. All right, so now in Desmos, which is super cool, we used to have to learn to graph this crap by hand when you had multiple angles. Now that we have graphing utilities that are so great, no one in their right mind asks students to learn these things by hand anymore. But yeah, there's all these painful techniques on how to graph multiple angle trig equations.
Ooh.
So you get this thing that they call a rose. How many petals do we have? 4. So let's notice a couple of things. So let's change it to sine. All right, so we've got these 4 petals still.
They changed.
Now, yeah, they changed, they rotated. For sure they rotated. So notice that, keep that in your mind. The coefficient inside the angle was even, and we had double the petals. Now let's put an odd in here, and we get exactly the number of petals, right? Whether it's a sine or a cosine, we're going to get exactly the number of petals. And yes, they rotate. And if we take the minus, you'll get a different rotation. If you take the minus away. And if you change that to a bigger number, you get a bigger radius, if you will, for each petal. So now notice that this goes from 0 to pi, and even if we went 0 to 2 pi, we're still going to get the same 3 petals. So, but what you have to keep in mind, if this looks identically the same, whether I put a pi or a 2 pi there, what do you think is happening?
It doubled it.
Yeah, they're being traced out twice, right? They're being traced out twice. So if we go back here to even, and I only do half, I'm not going to get the full, like we need to go all the way to get all the petals. All right, so not super important, but it's just an observation. You can see it in Desmos really easily. If whatever this angle is, whatever this angle coefficient is, if it's even, you're going to have double the petals. And if it's odd, you have that exact number of petals, but it's because each petal is traced out twice. All right, so that curve is a rose. They call them roses or flowers or something. Roses usually. Some sort of flower, some petaled flower. They don't usually call them daisies
They should.
or tulips. Okay, now that is a polar curve. If we want to find the dy dx and figure out what the slopes of the tangent lines are, we convert to parametric. So here is how we convert to parametric. We do r cosine theta and r sine theta. So this is the r. I'll keep it in parentheses just to try to give it some emphasis. So r times cosine theta and r times sine theta. So that is the parametric representation of the polar curve. If you graph this, if you go to Desmos and graph this in parametric form, you get the same graph. They're the same, they're equivalent. Okay. Now there's no simplification that we can really do here because these angles are different, so that's not cosine squared. There's no double angle thing we would want to use here. That is our parametric form. If we want dy dx, if we want the slope of the tangent line, that's dy dx, we just have to differentiate this. So we're going to differentiate the x, we're going to differentiate the y. Both are products, so we have to use the product rule. So we're going to do first derivative second. I'll treat the thing in parentheses as first. So treat that as first, and the second is the function on the right. So the derivative of this function on the right is negative sine of theta. So we're going to have a negative times a negative, so it's going to be positive. We have cosine of 2 theta. And we said this derivative was negative sine of theta, so times sine of theta.
And then chain rule on the 2?
Um,
On the 2?
Not yet, because we did first derivative second.
Okay.
So we'll do chain rule now. So first derivative second plus derivative of first. Derivative of first is going to be, we're going to have to take the derivative of cosine, which is negative sine of 2 theta, times 2. So negative sine of 2 theta times 2 will have a negative and a negative. So those will turn into a positive, and then 2 times 4 is 8. So that's the first part, and then multiply, so derivative of first times second. Everyone agree on this derivative of first? Derivative of first here, that's going to be negative 2 sine of 2 theta. So that's going to be positive 8 sine of 2 theta. And then down here, same thing, first derivative second. So first, we can just rewrite, derivative of second is cosine. First first, derivative second. And now derivative of first, oh, that's the same, we already did that, right? So that's 8 sine of 2 theta times sine. Okay, and often there are some simplifications. In this case, I don't see any, but often there are. You don't need to. If our whole goal is to figure out what dy dx is somewhere, we don't need to simplify dy dx.
We can divide everything by 4.
Yeah, when it's.
I'm good.
When we fraction it, when we turn it into dy dx, so I would not even, you don't have to on the test, you don't have to write this whole thing out. You can just say this. This is totally fine for me. You don't need to like just recopy the whole thing over. You know, like some people try to be efficient and write the y prime up top and the x prime down below and then just put a line through it. I mean, whatever. You could just do this. That's fine. You don't have to rewrite the whole thing. Because the goal here, it's not asking us for a simplified form of dy dx. The goal here is just figure out the slope of the tangent at that point. That's what we want. So let's figure it out then. So dy dx at, so this doesn't have any r's in it, does it? Right, just theta? So we can really just get away with saying at theta equals pi halves. That's all we have to do. So now we're going to do the fraction. The numerator is the y prime. So we're going to plug in pi over 2 for every theta that we see. So we have a 2 theta here. So we have to plug it into all of these. Pi over 2. Now let's notice that if we plug in the pi over 2 right here, we're going to get a sine of pi. And sine of pi is 0. So that one's going to go away, as will this one, right? Up here? Because pi over 2 going in here is going to be a sine of pi. Sine of pi. So those are going to both go away. So we don't have to worry about those anymore.
And then the cosine.
And cosine of pi over 2 is 0. So this is going to go away also. That's all going to become 0. So the numerator is going to become 0. So now we just have to make sure the denominator is not 0 to conclude that the overall tangent value is 0. So let's check. So we get a 0 down below. So y prime, and down below, I mean this equation here, which is the numerator. And then we go x prime in the denominator. So plug in pi over 2 here. Sine of pi over 2 is 1. So that we can kind of ignore. And this becomes cosine of pi. Negative 1 multiplied by 4, so we get negative 4. So we get 0. So what does that tell us about the graph of this function at that point? Horizontal tangent line? Right? So if we look at the graph of that one, negative 4 cosine of 2 theta. So negative 4 cosine of 2 theta.
And
You're missing the equal.
Oh yeah, I need that. So there we go. So let's figure out where we are. So if we want to figure out where we are, we look at the original function. Let's figure out where we are. So when theta is pi over 2, well, this should just give us 4, right? If we plug in, let's just confirm it. If we plug in pi over 2, we get cosine of pi, which is negative 1. Negative 1 times negative 4 is the 4. So 4 comma pi over 2. We should just visually be able to see where we are. We go to pi over 2, and we go out 4. So pi over 2 out 4, we're right there. And yes, we have a horizontal tangent. Everyone agree with that? So it's just giving us what we expect. So that horizontal tangent that we are finding is at pi over 2. So there is our corresponding horizontal tangent right there. All right, let's go ahead and take a break, and then we'll finish up chapter 12, section 3.
Yay.
Yeah, now we get to review for the final.
It's gonna be so fun.
After we learn how to integrate.
That was the part.
After we learn how to integrate.
What percent of our final is gonna be polar color?
25%. 25% from chapter 12. 25% of the final exam 1, 25% of the final exam 2, 25% of the final exam 3, 25% of the final chapter 12.
No.
Yeah. It'll be split. 4 questions from each.
Easy ones, right?
Yeah, I'll pick the simplest ones.
Are you joking or not?
I'm joking. Something that seems simple for one person may not seem simple for another. Right?
I know with the parametric equations, you should do like, Earth polar equations, you should do like R equals 3.
And then find the horizontal tangents.
know what? But clean now, goddammit. I keep hitting that, you know. Anyways, what do you think? What? So hypothetically, we got time travel Zamboni that when it hits 88 miles per hour, travels in time, and somebody fails the calc test. So you fire up the time travel Zamboni, and you shoot into the classroom fully on the Zamboni. Do you think the future version of yourself would be able to take your test?
How far in the future we're going, man?
I don't know, as far as you like.
Cause like if you go like career far, no. Like 5 years, you're in the field, no longer in school, absolutely not. You go like senior year, 100%, I got no doubt.
We'll ask them, because this is very pertinent
We're
information.
not talking like, could you complete the test? We're saying legally, would the school allow you
Oh,
from the
legally?
future to take your own test?
As long as you pay them, I don't give a shit.
Yeah, you pay them, man, they make it happen.
Yeah, no.
I look at them as I'm like, I am from 16 years in the future, I've been studying for 15 of those years, but here's 1,000 of your schmeckles, so let me do it.
This is worthless by my time.
It's completely worthless. This isn't even a single parchment of toilet paper, but you can have it.
Dude, that's gonna be my plan. First, invent time travel, then come back and pass the test.
Have you considered studying?
You don't study.
No, I don't, but that's because I'm good.
If you change your name, homie, you're good.
Yeah. To be fair, I thought he was chaotic neutral, so here we are. So purely hypothetically speaking, we got a time travel Zamboni.
Trying this one, okay.
All right, and then we got it up to 88 miles per hour, and we got it into this classroom, and time travel back. Could your future self say you're gonna fail that test, let me take it for you? Would that be allowed?
Could future you take your test for you?
I wanna see it happen. If that can happen, let's let it happen.
Do I just get an automatic A if I come back and I say, hey, I used your class to make a time traveling Zamboni? Will you just give
That's
me
a cool idea.
No, genuinely, if
But your
I
feet-
like leave and I come back with like a full beard, I can't grow a beard, a full beard,
Yeah.
and you look at me and I say, I made time travel a thing. But
Right.
I've come back so that I can get an automatic A on your final
Yeah.
exam because I've used your concepts for
But,
time travel.
but if you come back from that future place, you will have only been able to do that if you did well on the final.
Well, what if I bombed the crap out of the final and then studied for the next like 6 years to figure it out?
Hey man, if one of you guys figures out how to do time travel in my lifetime,
Yeah.
that would be
You
so
get
cool.
an A?
You can travel back in time and you'll give us an A.
I
the only thing I care
travel.
about,
I want to
Mark.
travel.
I do not care about time travel. I want an A.
I want an A.
You can have the
I'm only going to learn how to do time travel so I can get an A.
Yeah,
No,
that's
you
how it's
can
gonna
have the
be.
time traveling Zamboni, I just need the say.
No one-
Oh, whoops, did I forget to hit pause?
Time traveling Zamboni.
I'm so happy they get to hear this whole conversation. Immortalized.
Yeah,
on the internet.
Bryce is going to listen to it and be like, wait, what's happening?
Don't worry about it, Bryce.
Okay, so what do we think this curve is? So we have another polar curve, and that curve is a... So it's not a cardioid because the magnitudes of the coefficients don't match,
But it is a.
but it is a cardioid-ish thing, right? It's either got the bubble in the inside or it's flat. So this one is going to be one of those two. And it doesn't matter, but it's a polar curve, and we want to know what the slope and the tangent is at those 2 points, those 2 polar points. So our strategy, if we're given a polar curve and we want to do calculus on this polar curve, let's convert to parametric. Because if we convert to parametric, we can do dy dx more easily. So we take our x and it's going to be r times cosine of theta. And then we do r times sine of theta. Done. We've converted from polar to parametric. And parametric is nicer for calculus because we can find x prime and y prime and then form dy dx. dy dx is y prime over x prime. Once again, we are going to differentiate with the product rule. So we're going to do first derivative second. So first is this quantity in parentheses. Derivative of the second is negative sine of theta. I'll pop the negative to the front. So first derivative second plus the derivative of first is cosine multiplied by cosine. So if we want, we could write that as cosine squared. And then the derivative of y prime, same concept, we do first derivative second. So first derivative second is cosine plus the derivative of first is cosine multiplied by something fishy's happening. Oh no, multiplied by sine. I almost wrote cosine squared again. Everyone follow that? So we're up here, so first derivative second, and then derivative of first is cosine, multiplied by sine. I write it as sine times cosine. So now we've got our y prime and our x prime. Again, you don't have to rewrite and figure out what a simplified dy dx is. Just remember that dy dx is y prime over x prime. And let's evaluate. So dy dx at theta equals, the r doesn't matter, right? There's no r in here. So that's r comma theta. So we want theta equals 0. So we're going to come down here, we're going to plug in theta equals 0. And when we plug in theta equals 0, sine of 0 is 0. So that part's going to go away. All this is going to go away. Sine of 0 is 0, so all of that's going to go away. Everyone okay with that? So we're plugging in 0, so let's focus on the y prime first, because that's the numerator. So down here, when we plug in 0, that's gone, so we have 4 multiplied by cosine of 0 is 1, so we end up with 4. Everyone okay with that? And then we do x prime at 0. That part all vanished because sine of 0 is 0. Cosine of 0 is 1, so we get 4 divided by 1. So the slope of the tangent line when theta is 0 is 4. That's the slope of the tangent line. And then let's do the same thing at 3 pi over 2. So let's find dy dx at 3 pi over 2. So theta equals 3 pi divided by 2. Okay, 3 pi over 2, we have a slightly different set of pieces that are going to be 0. Let's see if we can figure it out. So at 3 pi over 2, cosine of 3 pi over 2 is 0. So cosine of 3 pi over 2 is 0, so this would be 0, all that would be 0, and all this would be 0. If cosine of 3 pi over 2 is 0, all that stuff goes away. So we're going to end up with, for y prime, looks like 0 in the numerator. We just have to make sure we don't have 0 in the denominator. So if we plug in 3 pi over 2 here, sine of 3 pi over 2 is negative 1. So 4 minus 1 is 3. So we're going to have negative 3 multiplied by sine of 3 pi over 2, negative 1. Important thing here is that the denominator is not 0. So we're going to get 0 as our slope of tangent, which corresponds to a horizontal tangent line. So those are the two slopes. So let's just draw the graph and make sure that this passes the smell test. Make sure that it smells smart. So 4 plus sine of theta. So if we graph, r equals 4 plus sine of theta, we've got that. So let's grab a picture. Come over here. Does it make sense? All right, so the first one was when theta was 0 and r is 4. So when theta is 0 and r is 4, I did that one in blue. So theta is 0, r is 4, so that's where we are for point 1. And if we draw the tangent line, there's our tangent line, slope is 4. So that makes sense. Second point is at 3 pi over 2, and then r of value of 3. So 3 pi over 2, that's this angle right there. And let's do this one in green. That's that one. So 3 pi over 2 is right there. We're 3 units away from the origin, so we're right there. The tangent line is in fact horizontal. That matches. So that's what's going on.
It's a very flat cardioid.
Very flat cardioid.
It's a fat boy.
Not circular at all.
It's not circular, not at all. Okay. Let's talk about horizontal and vertical tangents. We already know that a constant times sine or a constant times cosine is a circle, either tangent to x or tangent to y. We could figure it out if we had to. But we know it's going to be a circle, so in our minds we know there's going to be 2 horizontals and 2 verticals. All right, so we first convert to polar, from polar to parametric. So we do r cosine of theta, and we do y equals r sine of theta. And maybe in this case we'll rewrite them a little bit, so that's minus 2 sine theta cosine theta. And this one's going to be minus 2 sine squared. So we've converted our polar curve into a parametric form. And now we can find dy dx. And we want dy dx because that's how we find the slope of the tangent line. So let's find the derivative of each of these. Okay, so x prime, we're going to do product rule again. So first derivative second, the derivative of the second is minus sine of theta. So this will be 2 sine squared of theta, first derivative second, plus the derivative of first times the second. So that's going to be minus 2 cosine squared of theta. And for the second one, down here, we just use the product rule, or whatever it's called, power rule, in connection with the chain rule. So there is the derivative system, x prime and y prime. And then we remember that dy dx is y prime over x prime. So which one of those do we set equal to 0 to get the vertical tangents?
Cosine?
The axis. Yeah.
X's. So these are going to lead to vertical tangents, and these are going to lead to horizontal tangents. Everyone okay with that?
Because you want x prime to be or 0, so it's undefined to get a vertical.
Right. Now, if we get an indeterminate form, if we have a 0 for both, then we have to go into a whole limit process, which we're going to kind of avoid. And we know here we have a circle, so we're not going to have any concurrent zeros. So let's see. All right, so to find the vertical tangents first, we're going to set this equal to 0. And if we divide out 2, no problem, right? If we divide by 2. Okay. Well, then we can, there's a lot of ways we could do this. We could add cosine squared to the other side and then divide by cosine squared and turn it into a tangent equation. We could just factor this. Doesn't matter. Lots of different ways that you could do this. If we go the factor method, we've got that. And so that tells us that x prime is 0 when sine is equal to plus or minus cosine. So either sine and cosine are the same, or sine and cosine are opposites. That's the only way we're going to get 0. So when we think about the unit circle, for sine to be equal to plus or minus cosine, where does that put us angle-wise?
Diagonal.
So it's going to put us either at pi over 4, multiples of pi over 4 that are in these places, right? Those are the 4 places where sine and cosine are either equal or opposites of each other. So this tells us theta, if we wanted to write this concisely, we would say theta equals pi over 4 plus pi over 2k. So pi over 4 is the first angle, and then we add 90 degrees, add 90 degrees, add 90 degrees, and we'll get them all. So that's the solution of the first one. Okay, so when we look at this graph here, let's put the graph up there because it's going to be important to figure out which thetas actually apply. Not all the, we don't want all the thetas, we just want the thetas that make sense for this graph. So if we look at our graph, all right, so if we look at this graph, I want you to notice a couple of things. Let's just get it up here first. Okay, let's notice that if we go from 0 to pi, don't we get the same graph?
Yep.
So the period for this curve, the way we get exactly one loop is 0 to pi, not 0 to 2 pi. So that tells us that we only want the theta values that are between 0 and pi. So 0 to pi completes the circle. So theta, to complete this circle, theta is going to be an element of the interval 0 to pi, excluding the pi. That'll do one loop of the circle. So when we look down here, the thetas that we are going to pick are theta equals pi over 4 and
3 pi.
yeah, we just want these two. Those are the only two that are going to fall within this domain. So we're going to take pi over 2 and 3 pi over 4. And now if we want to figure out where we are on the circle at 3 pi over 4 and pi over 4, if we go back to Desmos, if we want to plug in here, I don't know if this will work. Well, we can do it in our head easily, right? Or let's do this. If we do, it's r comma theta. Can I do r of pi over 4? Will it do that for me? Let's just see. Is it going to plot that point? No, it's not going to do it for me. I wonder if I wrote this as r of theta. Would it do it? Oh, then it does it. Okay, so when we plug in pi over 4, sine of pi over 4 is root 2 over 2.
You get root 2 is r, and your angle is pi over 4. So those where the point is.
When we plug, it's not giving me the right, it's adjusting the point. I don't want it to do that. So you tell me, when I plug in pi over 4, what do we get there? So if we plug in pi over 4, what do we get as our r value? So if we do r of pi over 4, what do we get?
Right 2, negative right 2.
So this is root 2 over 2? Root 2 over 2, so it's going to be negative radical 2.
Yeah.
So if we go to pi over 4 here, pi over 4 is up there, but then we go negative root 2, it's going to bring us down to right over here.
Gotcha.
And that's going to be where we have a vertical tangent.
And you might have missed the negative in Desmos, which might be why I was giving you.
Oh, is that what happened?
2 sine theta, I think.
Oh, that's possible. That's possible. That,
How do you know it only goes to pi and not 2pi?
because if we look at Desmos, we can do it by hand, or it's just easy enough in Desmos to just adjust this right here.
Yeah, I was curious, like, not on Desmos,
Yeah,
basically.
Like,
test
if we're
wise, you
testing-
want us to put
So-
it all in.
If you're graphing this, think about it this way. Let's do what we did with the cardioids. So if we look at r comma theta, but usually we plug in the theta. So if we plug in theta equals 0, and what was it, -2 sine theta, so r equals -2 sine theta. If we plug in 0, sine of 0 is 0. So this is 0. So here's where we are when theta is 0. And if we plug in pi over 2, sine of pi over 2 is 1. -2 times 1 is -2. So if we go to pi over 2, that's up here. But it's -2, that's down there.
Yeah.
So we've graphed half a circle with pi over 2.
Yeah.
And if we go to pi, what we're going to see is that we're back to the origin.
Yeah.
So pi took us all the way around instead of 2 pi taking us all the way around.
So on exam, we would have to do that to know which of our theta values we need to record as the answer.
Right.
Cool.
Yeah, so we just need to know whether we go 0 to pi or 0 to 2 pi. And so these circles that are adjusted by being on one, tangent to an axis, it's always going to be 0 to pi. That'll take us all the way around.
It's the same thing as with the roses, right? It's a sine of an odd numbered theta.
That's true.
Theta is
So because
one.
it's odd, we did 2 loops of the circle.
So if it's even, you do 2 full loops. If it's odd, you do 1 loop.
That's right. Yeah, that's a good, that's right, 100%. Okay, so what about the other theta value? So we had 3 pi over 4. If we plug in, well, I guess we could just look up here. Let's just write it like this. R of 3 pi over 4, what do we get? So we plug in 3 pi over 4 there. Sine of 3 pi over 4 is positive root 2 over 2. And then the 2's cancel. So at 3 pi over 4, that's going to be over here in the middle. But then we're going to go backwards, and that's going to put us right here. And that will be our other vertical tangent. So at pi over 4 and 3 pi over 4, we'll get those 2 vertical tangents. So that,
And so you want us to write them as an ordered pair of -√2 comma.
this is just going to ask where the vertical tangents are. If it also says, this didn't ask to graph, I'm just graphing it just as extra reinforcement.
It
That,
says find the points. So would you want us to?
so if we want to find the ordered pairs,
Yeah.
we would
Plug
do,
those numbers in.
and then the R value.
To get
Yeah.
that value? Like-
Yeah, so if we wrote them, how would we write them then? So this one we would write as, what would be this ordered pair?
-√2.
-√2, 3 pi over 4. So that would be the point of tangency here. And then up here, the point of tangency would be -√2 comma pi over 4. Yeah, so if you're asked for the point where you have your vertical tangent,
That's the actual.
then those are the actual points, yeah. Now let's look for the horizontal tangents. Horizontal tangents, we're going to set this equal to 0 here. We can divide out the -4. And that's pretty easy. The only way sine times cosine can be 0 is if one of them is 0. So this tells us that sine is 0 or cosine is 0. And if we look at our unit circle, this tells us that we are either at these 2 quadrantal angles or those 2 quadrantal angles. But once again, we notice that the domain that creates this curve is 0 to pi, excluding pi. We don't want to double up on that point. So we exclude the pi. So now we look down here and we say, okay, which of these angles are in this interval? And it's those 2. Pi we're going to exclude because it's going to repeat what happens at 0. So the thetas that we are going to choose here are theta equals 0 and theta equals pi over 2. So those are the 2 that we're going to choose. And if we wanted to write these in polar form, we would say, okay, the R value, let's see, we already did those, I think, over here. So the R value at 0 is 0, and the angle was 0. That's a polar point, the origin. And then the R value at pi over 2 is -2, comma, pi over 2. So these would be the two polar points. There we go, the two polar points. So if we look at our graph, those two polar points are going to correspond to horizontal tangents. So 0, 0 is right there, and pi over 2, -2, so that would put us down here. So those would be
Wowzers.
What was the question?
There was no question.
Oh, that wasn't a question. That was just a grunt. It's just a sound.
Wowzers.
Wowzers.
That's a lot.
That's a lot for a circle. Now you can, if it just says at what points do these happen at, you could represent these points in different ways. Like here I represented them with polar. You could represent them in Cartesian unless it says represent with the polar point. So it doesn't this one's a little bit vague. It does say polar curve, so it kind of means you probably should pick a polar point. But it is a little bit vague.
If you know what the circle is, it's very easy to just figure out what
The Cartesian points
coordinates
are.
for the
Yeah.
verticals and horizontals are.
Yeah. So I would say if it does give you polar, give it in polar. Okay, now let's do a hard one.
That was easy.
So,
We'll see.
cardioid, right, that's a cardioid because the magnitudes of the coefficients are matching. So, this cardioid we need to go all the way around from 0 to 2 pi to get the full cardioid. And here's the piece that I want you to think about before we actually do the math. How many vertical tangents do you think there are?
2, 3, 4, maybe 4.
I've heard a couple different numbers.
3.
Maybe.
So certainly we are imagining a vertical tangent here.
At least 2.
Right, at least 2. We're imagining a vertical tangent there. Horizontally, we're imagining a horizontal tangent there. We're imagining a horizontal tangent there. Imagining a horizontal tangent there. So in the dimple, the question becomes, and what we will see, is that we are going to have both x prime and y prime being 0. We are going to see that we have an indeterminate slope of tangent line at that origin, at the origin in this case, wherever the dimple happens to be. We are going to get dy dx is going to be 0 over 0, so you have to do a limit process. We're not going to do the limit process. It's kind of a hassle. It's in the book. You can look it up. What's going to turn out is this. All these polar curves seem to have a lot of symmetry. If there's 3 horizontal tangents, there's also going to be 3 vertical tangents. It's going to turn out that the dimple has slopes that are becoming vertical so fast that this will in fact, this will in fact end up being a vertical tangent.
We could exhaust the limit.
I should have drawn it in black though. So if you do the limit process, you will get that dy dx is undefined there.
Yeah.
So dy dx is y prime over x prime. X prime is going to go to 0 faster than y prime. The bottom is going to dominate and you're going to get an infinite slope of tangent, which will be undefined. So we will get 3 of each. All right, so we'll just assume that going forward. Let's not deal with the limit process. Okay, so to do this, we are first going to convert our polar curve over to parametric. So we want our polar curve converted, so all we do is take the polar curve and multiply it by cosine for x. Take the polar curve, multiply it by sine for y. Okay, now we find our derivative system. So we've got our x prime to be found and our y prime to be found with the product rule. Same as the last couple. Product rule, we do first, derivative second. So again, let's treat the quantity in parentheses as first and the second as the function on the right. So first derivative of second here is minus sine. So if the derivative there is minus sine, I'm going to distribute the negative sign and put a sign right there. So there's first derivative second. Plus the derivative of first times the second. The derivative of first is negative 3 cosine of theta. And if we multiply by second, then we're going to get a cosine squared. Y prime, same idea. We're going to do first derivative second. The derivative of second here is cosine. So that's first, derivative second. Now we do derivative of first times second. The derivative of first is negative 3 cosine of theta. So negative 3 cosine of theta times sine of theta. Negative 3 cosine of theta multiplied by sine of theta. So there's our derivative. Derivative for each, and once again, let's not rewrite dy dx out in long form, that's a pain in the neck, but let's just think about it like that. dy dx is y prime over x prime. Y prime being 0 is going to lead to horizontal tangents. X prime being 0 is going to lead to vertical tangents. So we're going to set each of those equal to 0. Now the thing with the cardioid, we did go 0 to 2 pi to get the whole cardioid. So we don't have to think about that half domain thing of chopping from 2 pi down to 1 pi. So let's set these to 0. So let's go y prime equal to 0. So this is going to be looking for horizontal tangents. We'll find those first. So y prime, set it equal to 0. So we are going to end up with negative. We can divide out negative 3, right? Negative 3, negative 3, negative 3. So if we divide out negative 3, we're going to end up with 1 plus sine of theta times cosine of theta plus cosine of theta sine of theta equals 0. Everyone okay with that? So we divide it out, we set it equal to 0 and then divide it by negative 3. So here we want multiplication. The only way to solve a trig equation is to have multiplication equal to 0 so you can use the 0 product rule. What is common to both of these terms? Cosine. So we factor it out. So regular algebra stuff where we factor that out. So we pull the cosine out. We're left with 1 plus sine, which is 1 plus 2 sine. So we've got that. 0 product rule says if you have a product equal to 0, one of them is 0. At least one of them is 0. So cosine is 0 or sine is equal to negative half. So those are the options for theta. We go to our unit circle. Anytime we have a basic trig equation, you should be going to the unit circle. So sine of theta is negative 1/2. If we look at the 12-sector circle, that's where sine is negative half. Cosine is 0. It's right there and right there. So we have 4 angles between 0 and 2 pi where y prime is 0. Those 4 angles, let's just look at those 4. Let's not write the general solution. The 4 are going to be pi over 2. What angle is that one?
7 pi 6.
7 pi over 6, 3 pi over 2,
11.
and 11 pi over 6. So those are the 4 angles between 0 and 2 pi. Note that these are finding horizontal tangents, and we only have 3. One of them is going to be a repeat 0 for x prime, but x prime is going to win, and it's going to get the tangent line for it. So let's do that. So let's come over and set x prime equal to 0. So x prime equals 0. So x prime is the top one, so we're going to have 3 plus 3 sine of theta minus 3 cosine squared theta. Oh, I forgot to divide out the 3. Let's divide out the 3. So all these become 1s. And I'm going to distribute here. So I'm going to have sine of theta times 1 plus sine of theta times sine of theta minus cosine squared of theta equals 0. Trig equation. We want to turn it into multiplication. Well, we can't factor here because there's not a common factor like there was there. So we need to convert one trig function into the other. Which one do we want to turn into the other one? Because there's a sign that's over here, so if we can't convert a single sign over easily. We know that sine squared plus cosine squared is equal to 1. So cosine squared is 1 minus sine squared. Now we can combine like terms, and we're going to end up with 2 sine squared of theta plus a single sine of theta minus 1 is equal to 0, which is factorable. And that is a simple quadratic that's going to factor really easily because you have literally no choices. It's got to be 2 and 1, because that's prime. It's got to be 2 and 1. 1, the only way is a 1 and a 1. And now we just have to make sure that we put the plus in the right place. The middle is positive, right now is 1 sine of theta. The outer is 2 sine of theta. We want that to be preserved, so we're going to put it here so that we get the bigger one with the plus. So this tells us that sine of theta is a half, or sine of theta is -1. So let's figure out where these thetas are. So sine of theta is positive 1/2. That's going to put us at these 2 locations. Sine of theta is -1 is going to put us at that location. Ooh. There's our duplicate. So we have theta equals pi over 6, 5 pi over 6, and 3 pi over 2. So here is the duplicate. So we've got the duplicate right here, 3 pi over 2. So that tells us that dy dx is 0 over 0. Then we have to take the limit as theta goes to 3 pi over 2, and you figure out the limit. That one over there is going to win. X prime equals 0, that's going to win, so that's going to give us a corresponding vertical tangent. So now we can list everything. So our horizontal tangents, if we list them as 3 ordered polar points, so it's r comma theta, we've got our thetas, pi over 2, 7 pi over 6, and 11 pi over 6. 11 pi divided by 6. So we've got our 3. if we want to get the R value, we can look at the original equation. We probably can look at just look at the graph even. So our first theta value was pi over 2. So pi over 2, and what's going to be the R value there? 0. If you plug this in, you also will get 0. If you plug in pi over 2, sine of pi over 2 is sine of pi over 2.
Oh, wait.
Sine of pi over 2 is 1.
I think
Oh, these
it's-
are horizontals. These are horizontals.
Yeah.
Yeah, these are horizontals. So the horizontal,
Is gonna be your negative.
-6, right? If we want to get to that horizontal, if we're at pi over 2, that's going to be -6. -6.
All the way down.
Yeah. And then 7 pi over 6, that's going to be over here. So this looks like, how many? So 7 pi over 6
Looks like
is right there. This looks like 2, 4, it looks like,
it's probably 5.
it's 4.5, I think.
No, yeah, it's 4.5.
I think 4.5.
Yep, 4.5.
But let's just check, if we plug in 7 pi over 6 here, we're going to get -3 minus 3 times sine of 7 pi over 6 is -1/2. So this is going to be -3 plus 3 halves, which is negative, what is that? That's -3 halves. So that's actually corresponding to this one over here, but that magnitude does not feel right. The magnitude does
We're on
not.
horizontal tangent still.
Oh, we're on. Ah, dang it. We're looking at the greens. We're looking at the greens. So when we go to 7 pi over 6, we're going to go backwards 1.5 right there. -3 halves is right there. So that's that one. So -3 halves. Oh boy, that's complicated.
Something tells me the other one's 3 halves.
And so when we go to 11 pi over 6 here, sine of 11 pi over 6, isn't that also -1/2?
Yep.
So that's going to give us the same -3 halves value. So when we go to 11 pi over 6, we're over here. And then we go backwards, same thing, we go backwards 3 halves. So that'll give us that one. Okay, so there are the horizontal ones. The vertical ones, yeah, maybe it's not the best idea to try to just look at the graph and pick them up. It might be just easier to plug them in. So our angles here are pi over 6, 5 pi over 6, and 3 pi over 2. Yeah, let's just plug them in this time. So what was it, negative and negative? So I'm going to rewrite it down here just Okay, so if we go to pi over 6, sine of pi over 6 is 1/2. So we have -3 minus 3 halves.
4.5.
So it's -4.5, which is -9 halves. When we plug in 5 pi over 6, sine of 5 pi over 6 is also 1/2. So we get the same thing. When we plug in 3 pi over 2, sine of 3 pi over 2 is -1. So we get 0. So that'll be the 3 verticals. So 0, 3 pi over 2. We come to 3 pi over 2, but then we go 0. That's going to be our vertical tangent. Question?
What if it asks for all 45-degree angle tangent lines?
Ugh. Then we would set dy dx equal to whatever we need it to be equal to.
Yeah, so it's equal to 1 or negative.
1 or -1.
So, and then you solve for 1.
And then solve. This is hard enough, I think.
Slope of 1 is a 45-degree line.
Okay, any question on any of those?
So -1 is 45 the other.
So this is one of those things that's not implicitly difficult, but it's implicitly complicated.
It's a lot of stuff.
There's a lot of steps. So look at these carefully because you want to be able to do them.
Yep.
Okay, let's go to our last topic, which is area. So the area bounded by a polar curve is a little different than area beneath a curve. when we say beneath a curve with a rectangular curve, you're sort of thinking literally beneath the curve and above an x interval or below an x interval if the curve is negative. So with polar, the idea is that we have a slice, like a sector, and we're trying to find the area that's between two theta values. So it's going to be like a windshield wiper, and we want to find the area in between. So long story short, we're going to use Riemann sums, and each one of these polar regions can be approximated by a circular sector. Everyone see that? These are circular sectors. These are polar regions. These polar regions are approximated by polar sectors. As theta gets compressed closer and closer to 0, the polar sector, the polar region's approximated by the circular sector better and better. So same Riemann sum idea. It all boils down to knowing how to find the area of a sector. And the area of a sector is this right here. Area of a sector. 1/2 theta r squared. So in this case, their theta is called delta theta because we're supposed to visualize it as being very small. But 1/2 theta r squared. That is the area of a sector, of a circle. So the total area then, we're going to add up all the sector areas. So it's 1/2. So the basic formula in your mind should be 1/2 theta r squared. The theta here is being represented by a delta theta because we're imagining it as very tiny. F, they love to introduce a new letter. You could just think of this as r of theta sub k asterisk. So this is 1/2 theta r squared. 1/2 theta r squared is the area of a sector. Add them all up. You'll get a good approximation. If you let the number of circular sectors increase towards infinity, you get better and better approximation. And then if you do the magic wand thing and take the limit of this Riemann sum, bada bing, you get the area formula. And what they've done here is generalize the area formula, and they're subtracting off this piece in here. They're subtracting that off. So they're saying, well, let's not just assume that we're zooming all the way back to the origin. Let's imagine that we have two polar curves that are trapping this region here between two thetas. So this is going to be, if you did 1/2 f squared d theta, you would get the area of all the way in here. And then you subtract off the 1/2 g squared d theta, you get that, and you get the stuff that's left in the blue. So they just generalize it there for us. So here is the formula, though, that we want to be thinking of. The area of a sector is 1/2 theta r squared. Theta, though, is the small theta, so that's going to correspond to d theta. And then r squared is the distance from the origin out to the polar curve. So that is the formula you need, 1/2 theta r squared.
Are you gonna make us rotate these?
No!
Okay, great, thank you.
No. Oh my God.
Thanks for being friendly.
That would,
R to the
rotate that around a random line.
Please don't.
Oh my God, that would
Please don't.
be really exciting and dramatic.
Just thinking about it's giving me a headache.
Okay, so speaking of headaches, so here we have a lemniscate, which is the infinity symbol. That's the equation that generates the lemniscate, the infinity symbol. And we want to find the area inside one lobe, one side. So we want that area right there. So we need to figure out what the theta interval is. So before we do anything, we need to figure out what thetas are important here. And if you just look at the graph, it certainly looks like this point right here is, well, let's first find out, where are we at theta equals 0? If we plug in 0 right there, where are we? Yeah, so we're just at 1, right? So theta, so 1 unit away from the origin puts us right there. So theta is 0 right there, 1 unit away, and then we start rotating. When we plug in theta equals pi over 6, we're going to be right there. When we put in theta equals pi over 4, that's this diagonal one right there. Doesn't that look like we're back to the origin? Right, it looks like we're going to go 0 to pi over 4 to get this upper piece of this right side. And that is all we really need.
Multiply by 2.
Because then we can double, if we find that, then we double it. And we've got the blue. Say again?
And we don't have to worry about negatives or.
And then we don't have to worry about negatives and reverse quadrants. So let's just double check. When we plug in 0, we get 0. Excuse me. When we plug in 0, we get 1. When we plug in pi over 6, just as a check, plug in pi over 6 there, we're going to get cosine of pi over 3, and cosine of pi over 3 is 1/2. And we have to take the square root of 1/2, so that's going to end up being 1 over root 2. Now let's plug in pi over 4, and when we plug in pi over 4, we get cosine of pi over 2, which is 0. So sure enough, and we could double check on Desmos and look at some more intermediate points if we wanted, but this part is going to be graphed from 0 to pi over 4.
Did you do negative pi over 4 to pi over 4?
Yep.
Okay.
So if you did negative pi over 4, if you did negative pi over 4 to pi over 4, you get the whole right-hand side.
Yeah.
Yep. Usually with limits of integration, we like to have a 0, because it's usually easier to evaluate, but you could absolutely do that. So now what we're going to do then is say that the area is going to be 2 times integral from 0 to pi over 4 of 1/2 theta r squared. Well, by theta we mean d theta, we mean miniature theta, and r squared cosine of 2 theta. So we're using 1/2 r squared d theta. That's the area of a sector. And let me just put an integral there. I'm going to write it that way. That's it. So the 2.5 cancel. Integral of cosine is sine. But we have to use reverse chain rule. If we integrate cosine, we get sine of the same angle, but then we have to differentiate the angle and divide. And then 0 to pi over 4. Plugging in 0 gives nothing. So if we plug in pi over 4, we get a pi over 2, and sine of pi over 2 is 1, so we get 1/2. So the area of that right side is 1/2. And if we wanted the total area of both those eyeballs, we get exactly 1 unit. Shockingly, a rational number will be the area inside of that shape. 1 square unit. Totally unexpected.
Almost as if someone chose these questions to be easier.
Right? Almost as if we're cooking.
Well,
cooking
just
it.
the generic lemniscate gets you 1 though.
I know.
That's just the basic.
The basic lemniscate gets you 1. Okay, let's look at a cardioid. So quick graph of the cardioid. In our minds, we think start at 0. Sine of 0 is 0. 0 plus 4 is 4. We're 4 from the origin. Pi over 2. Sine of pi over 2 is 1. 8. Pi. 3 pi over 2.
0.
And we know it has to be 0. It's got to be right in the middle. Okay, so, and then when we graph this, it bubbles out and kind of is circular near the top, bubbles out, and it's kind of circular near the top. I can do better than that. Okay, so there is our cardioid. And we want the region inside the cardioid. So we want the area of that cardioid. Now in Calc 1, you're always told to avoid cusps. And in Calc 2, that's usually the best thing to do is to avoid the cusp. Many times with cardioids, you can integrate straight through the cusp and it just doesn't matter. But to be safe, it's better to just avoid the cusps. So instead of integrating from 0 to 2 pi, it would be better to go from negative pi over 2 to pi over 2 and double it, or from pi over 2 to 3 pi over 2 and double it. It's usually the better strategy, just in case. You don't have to worry about any points where there's non-differentiability. So let's integrate then. Let's do the negative pi over 2. And if you're not 100% convinced that that's where you are at negative pi over 2, check. Plug in negative pi over 2. Sine of negative pi over 2? Negative 1. 4 minus 4? 0. You're at the origin. So you are where you think you are. And then pi over 2 is going to put you on top. And again, you can plug it in and check. So negative pi over 2 to pi over 2 is we're going to get this area, and then we're going to double it. So I'm going to put a 2 in front to double it.
Are you sure you can still do that even though Scott's symmetrical against the x-axis?
Yes, we can do that, but it's symmetric about the y-axis.
Okay.
So as long as we do this whole right side, the symmetry will be around the y-axis. Okay, so then we have 1/2 multiplied by r squared. R squared is this hideous thing, so we have to square it. We're going to get 16 plus 16 sine theta plus 16 sine, I guess I could have factored out the 16, right, or the 4, plus 16 sine squared theta. D theta.
Would be 32 something?
Maybe, yeah, something feels funny.
The middle should be 32.
Oh yeah, that should be 32. Yeah, that should be 32. I can foil, I promise. I know how to foil. So then let's factor out the 16. The 2's cancel, factor out the 16. And what do you think we're going to have to do with that sine squared? So factoring out the 16, we're going to get 1 plus 2 sine of theta. What are we doing with the sine squared? Power reduce, downshift. So sine squared, what does that equal to if we power reduce it?
2 sine cosine.
2 sine cosine is the double angle for sine. That's sine of 2 theta, not sine squared.
1/2.
So 1/2.
1 minus cosine?
So 1/2 minus 1/2 cosine of 2 theta. Power reduction identity. And if it was a cosine squared, we'd add instead of subtract. So that is the power reduction identity from week 1. So long ago. Now we can integrate because we don't have any powers in there. So we're going to have 16, and if we integrate, we've got the 1 plus 1/2, which is 3/2. And if we integrate 3/2 with respect to theta, we get 3/2 theta. If we integrate sine, we get negative cosine of theta. And then we integrate this over here. We integrate cosine, so we're going to get sine of 2 theta. But then what do we do with that too? Divide, because we have to use reverse chain rule, so that's going to be a negative 1/4 out in front. And that will go negative pi halves to pi halves. Okay. This term right here contributes nothing because in both cases you get sine of pi or sine of negative pi, which is 0. Cosine of pi over 2 and negative pi over 2, those are both 0. Right? Cosine pi over 2, sine negative pi over 2. Cosine pi over 2 and cosine negative pi over 2, both are 0. So the only term that's not 0 is this first one. So if we multiply these, we get 24 theta. And that's going to be pi over 2 minus pi over 2, which will be plus. So we get 24 times pi.
Wait, isn't the sine of pi over 2 1?
The sine of pi over 2 is 1, but this is going to be the sine of pi because we have 2 times theta.
Okay.
So if we plug in pi over 2 there, we get sine of pi. But then when we plug in the pi over 2 here, we get cosine of pi over 2. So cosine of pi over 2 and sine of pi are both 0.
Okay.
Cosine pi over 2, sine of pi, blah, 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 blah. That.
Yippee.
Yippee, 24 pies. 24 pies.
Tasty.
You eat that if you really, really fat.
Mm-hmm.
If you eat 24
Gobble, gobble,
pies
gobble.
all at once, you'll be fatter than the Titanic.
Oh, really?
No, I feel like there are fatter.
That sounds like an integration problem.
Well, that's not.
Okay, so 24 pies. Let's do one more problem. So the region inside all the leaves of the rose. So there's the graph of the rose. Let's figure out our limits of integration. We plug in 0, we're right at the origin. And what do you think the angle is that's going to give us this point right there at the tip of that petal? Pi over 4, dead center of quadrant 1. Plug it in, pi over 4, you get sine of pi over 2. Sine of pi over 2 is 1. 1 times 3 is 3. That is this distance right there. So if we integrate from 0 to pi over 4, and then multiply by 8, because we're going to get this area of half a petal first. So our area, come on. Not now. So we get 8 multiplied by the integral from 0 to pi over 4. And then it's 1/2 r squared d theta. 1/2 r squared is that thing squared. So 9 sine squared of 2 theta times d theta. That'll give us our total area. So all the constants come to the front. So we get 36 out in front, 0 to pi over 4. What do we do with the sine squared?
Power reduce.
Power reduce. So we get 1/2 minus 1/2 cosine of.
Or 4 theta?
We have to double the theta. Every time we reduce the power, we double the theta. So 4 theta. Let's factor out the half and integrate. So if we factor out the half, out in front we're going to have 18. And then let's integrate. If we integrate 1, we get theta. If we integrate cosine, we get sine of the same angle. But then what do we do with that 4? Divide by 4, so minus 1/4, 0 to pi over 4. So integrate cosine and get sine. Reverse chain rule says divide by the 4. We already factored out the half. Half turned that 36 into a 16, so there's a 1 in the front there. Now, this term is 0. Whether you plug in pi over 4 or whether you plug in 0. Right, you get sine of pi or sine of 0. So both of those vanish. And plugging in 0 here also vanishes, so we end up with 18 times pi over 4. So we're going to get 9 pi divided by 2. That'll be the total area. Total area. Question?
For determining the limits of our integration on that four,
Yep.
are we going to be given that graph? The graph of...
If I was going to ask you to find any area that involved something other than a cardioid or a circle, you will be given the graph. Yeah, absolutely. Yeah, for any rows or how about something like that? So this says the region inside r equals root cosine and outside the circle. So that circle is centered at the origin. So it says outside the circle and inside this thing. So the region here that we're going to find, which we'll do on Tuesday, will just be that crescent right there. That's outside the circle and inside that thing.
You have to set them equal to each other.
So if we want to know what this angle is right here, we can tell from the graph that it looks to be pi over 3, but we would set the two equal to each other, solve and get theta is pi over 3,
And then you get cosine of a half.
and then we're gonna find the area of that, which we'll do on Tuesday, and double it. 0 to pi over 3 doubled. Okay, no more new content for me.
So that Scott just here got 57 pages of notes.
You only have 57? Yeah, small.
It's true.
57 pages.
57 pages.
I did 2
I have
notebooks.
562.
2 notebooks?
That's, you got 5.
2 notebooks.
560